So, welcome back to our video lectures on projective geometry. In a certain sense, the lecture that comes now is a kind of showdown for the first part of lectures that we had in our projective geometry class. In this lecture, more or less everything comes together, what we were dealing with before. So we will talk about homogeneous coordinates, about the axioms for projective planes, about von Staudt constructions, about small little incidence theorems, and what we are going to prove is that whenever we have a projective plane that satisfies one additional property, from that projective plane we can construct an underlying field. In case you haven't listened to my video lectures about von Staudt constructions and about 5 small useful incidence theorems, I warmly recommend that you watch them before because we will need what we did there in this lecture here. So, what are we going to do? Let's first start with what we already did. So we proved that whenever you have a field, we can, from that field, construct a projective plane, and the idea behind that was to do homogeneous coordinates. We did that in one of our very first lectures. And now we will talk about the opposite direction, and the direction in which we are going to head will be more or less the following statement, which is the reverse of what we had before. Every projective plane induces a field K. Unfortunately, I cannot prove this statement in this lecture, and there's a main reason for me not being able to prove it here, because it is simply wrong. So the statement as I've written it here is not true. There are counterexamples, but there is something to that statement that makes it not being far away from truth, because you just have to add one more ingredient to make it a true statement. So let me add this one more ingredient. Every projective plane in which P holds induces a field K. So you may remember that P was our shorthand for the statement that Pappus theorem holds. So Pappus theorem is a certain incidence statement, and we assume that it holds in our projective plane that we have here. So here's the incidence configuration for this statement, saying that whenever you have all the collinearities in that picture except for one, then the last one is satisfied automatically. Pappus theorem may hold within a projective plane or not, and if it holds, then you can construct a field from the projective geometry, and the purpose of this lecture is to show you how that works. So let me start from, by collecting the basic things we are going to prove. So assume that you have a projective plane, and in addition you have Pappus' theorem. Then it turns out that this structure will induce a field structure. You may remember from the last lecture that Pappus' theorem somehow is very strong. In particular, Pappus' theorem implies Desargues' theorem. So one may ask, well, what happens if Pappus doesn't hold, but only Desargues' theorem holds? Then indeed what you get is not a field, but you at least get something like a skew field. A skew field is an algebraic structure extremely close to being a field, but you don't have commutativity for the multiplication. So in that sense, we are going to try to use Pappus' theorem in our proof as sparsely as possible in order to, as a kind of side effect, also obtain the theorem about the skew fields. So let me first recall what exactly is a field. So a field consists of a set of objects, you usually call them numbers, and two, well, operators, plus and the product operator that operate on pairs of numbers. So plus takes a pair of numbers and gives you back a new number, and times also takes a pair of numbers and gives you back a new number. And then you need many additional properties to make that a field. So what are these properties? The first of all, both of them should be a commutative group. Well, here I have be a little bit more careful. Actually, it's not K itself that should be a commutative group, but it's K with the 0 taken out from that set, because well, you are not allowed to divide by 0. Being a group, what does it mean? Well, you need neutral elements in both cases. So in the case of the addition, the neutral element will be called 0. In the case of multiplication, the neutral element will be called 1. You need the existence of inverses, and you need the laws of associativity and commutativity in both cases. And in case you don't have commutativity here, this is the reason why I put those two brackets here, then you will only have a skew field. So far, up to that point, plus and times don't interact, and for that you need two more laws that define how they interact, and these are the distributive laws. So, if we want to have a field structure at the very end, then we must somehow prove that our set K and the operations we define satisfy all those properties that are listed here. And so you imagine it may be a rather long lecture that I'm giving now. So first of all, let me explain where we will discover our set K here. So we are starting from a projective plane, and now we have to ask ourselves, if we just have a projective plane, what should that set K be at the end? And what it should be is the following thing. You fix a line L in the projective plane, and on that line L you fix a projective basis consisting of 3 points, and those 3 points, well, we saw via cross ratios, you usually extract numbers from those points, and we will mimic the behavior of cross ratios essentially. So our field L, our set that we will have in our field will be the points on that line, and we take away the element, this point that we labeled to be the infinite point. So this will be perhaps the first thing that you have to digest here. The field elements that we will construct are points on a line. So what will be addition and multiplication? You remember the von Staudt constructions that were a good tool that related somehow geometry to the algebra of addition and multiplication, and we will use definitions of multiplication and addition via von Staudt constructions. So what will we be able to use as tools for our proof? So I said we are only allowed to use the 3 axioms of projective geometry and Pappus theorem or Desargues theorem, and you remember that I showed you some useful incidence theorems, and here in that picture I ordered them in their order of strength. So Pappus implies Desargues is essentially equivalent to the scissors theorem, both of them imply the little Desargues theorem, and little Desargues implies Pappus theorem, and I will try to be as restrictive as possible in the use of those theorems. This means I will mainly use well, everything that comes from here to here, and only sparsely use the theorem of Pappus. Actually, we will need it only in one important point. One more historical comment here. This theorem here, which I told you it is the theorem of Hessenberg, was only proved in 1905. This was after von Staudt, and actually it turns out that this theorem of Hessenberg somehow simplified the whole theory, because it told people that you don't need both of these theorems as a kind of starting time point. One of them is enough. So what else are we allowed to use? We are allowed to use the von Staudt construction for addition and multiplication, and we will use them as a kind of construction procedure to define what we mean by addition and multiplication. So let me now a little bit more formally state what we are going to prove. So we assume that we have a projective plane in which also Pappus theorem holds. In that plane, we single out one line. So if we have that line, what we then will do is we will single out 3 points on that line, and these 3 points will play the role of a projective basis on that line. So we have a line, we have 3 points on that line, and if you want to think in pictures, then you may consider this line to be, well, the yellow line in that picture here, 0 and 1 being placed at one point, and it may be a good idea to think of infinity being very far out. But one important disclaimer at that point: whenever I will draw a picture in that lecture, and I will draw many pictures in that lecture, these pictures are only diagrams. Diagrams that should show you which incidences hold, which kind of parallelisms will hold, but you can completely verbalize and serialize what is drawn in these pictures and make purely formal written formula statements out of each of the pictures and out of each of the conclusions. The pictures I'm showing you are just diagrams, and please take them just as a kind of help to understand, to visualize what is actually going on. But on the other hand, these pictures are also extremely strong because they completely tell you which incidences have to be considered in certain situations. So this here is perhaps one of the first pictures here. Okay, so I take my line L, I take my projective basis, and now I can already define what my set of elements in my field will be. It will be all points in the line L except for the point at infinity. So, and for later use I will call that set here K derived from PLI. I should also specify which line L I mean, but at the end it turns out it doesn't matter which line and which projective basis I actually choose. So for that situation, I now define addition and I define multiplication by von Staudt constructions. So, and by define, I really mean define. So we don't know what multiplication is in advance, and we don't know what addition is in advance. We now define a multiplication and an addition on our set K in the following way. So you have our yellow line. So what must addition do? It must take 2 points, say x and y, and from those 2 points construct one new point which we call x plus y. And how do we do that? So we take an arbitrary line here and take an auxiliary point on that line. We draw those two connecting lines. So when I say draw, I mean, well, in your projective geometry, there is a unique join connecting those two lines. And from there, well, we have singled out our point at infinity, and we can single out one line at infinity through the point at infinity, and by that think of a kind of parallelism, and then we draw the parallel to that line through that point and get this here, and we draw the parallel through that line through that point, and we will get this, and we call this point here x plus y. Why? Once again, the reason why I'm being able to do that is not that I'm drawing in that picture. The reason is that I have this line on which I calculate. I have a point at infinity. At that point at infinity, I can single out one specific line that plays the role of infinity. From there on, I can speak of parallelism, and with respect to that parallelism, I can do this construction here. Similarly, for multiplication, I single out one special line through 0 here. I take a point, an arbitrary point here, and if you give me x and y, and you already know where the 1 is, I do the following construction, draw these two lines, make this parallel here, and draw the parallel here, and where this line here intersects the yellow line, I get my point x times y. And if I do so, and define multiplication and addition in that way, then, big theorem, this structure is a field. And now we are going to prove that this is a field. So let me sort out what we have to do and where are the problems. So you may have already recognized the first problem that arises is the question, are my operations even well defined? So are they reasonable? Do they define an operation? Because if you look at those operations, they were not strictly defined just by x and y. I had two choices, two free choices there that were involved in the construction of x plus y. One of the free choices was which line do I take here, and the second choice was which point on that line do I take here. So does this matter or doesn't it matter? So let's have a look at that. So assume I choose a different point on those lines, then we would not have constructed our x plus y with respect to this red point. We may have constructed it with respect to that blue line, blue point, and may have ended up at a different point here. But there is a reason that we can say it will end up at the same point here. Because if you look at this configuration here, this little part of the drawing, this and the two parallel lines here, they are what we call the scissors theorem. And well, as soon as we know that this arc theorem holds, we also know that this theorem holds. So this line here has to be parallel to this one here, and ultimately this last incidence has to be satisfied automatically by the scissors theorem. So we can say, well, the choice of that point here really didn't matter. So did the choice of the line matter? So let me show you what happens if we choose a different line. So we may have chosen a different line. We already saw the choice of the point didn't matter, though we can take any convenient point on that line. So let's take the point that is located here and see what we get. We get that drawing, and we see that those two lines here have to coincide this time, because we see a little Desargues theorem in that picture. So you may recognize the Desargues theorem. There were three parallel lines, and we had two triangles, and we could conclude that the last incidence holds automatically if we have all the parallels here. So this time, by Desargues theorem, it also doesn't matter which line we choose. So taking all that together, we see that at least this operation up there is well defined. So how about multiplication? Essentially the same thing happens. So if you look at the multiplication, you could have taken a different point here, and again the scissors theorem tells you that you get the same multiplication result, and you could have taken a different line as well, and this time a big Desargues theorem tells you that you get the same points down here. So all in all, you can say, well, also the multiplication is well defined. So far we didn't take care of field axioms. So we essentially solved our first problem. So let's face the next one. We want to have a field, and if we have a field, we need neutral elements and we need inverses. The two obvious candidates are the 0 and the 1. So it would be good if we can find out that both 0 and the 1 are the neutral elements for addition and multiplication. But if you look at those constructions here, so if x were 0, your construction would ask you to construct twice the same line here, and finally drawing the two parallels would end up in the same point y. So 0 actually is the neutral element for addition. And similarly, if you look at multiplication, you see if x coincides with 1 in that construction, y must coincide with x times y in that construction. So 1 and 0 are indeed our two neutral elements. How about inverses? Well, inverses, you can construct them via reversing the von Staudt construction. I will exemplify that for the case of addition. So if you are given a point x, this one here, then the construction for minus x is such that, well, I just construct a point such that these two lines are parallel and these two lines are parallel, and all those incidences that you see in that picture are satisfied. If you do so, von Staudt construction tells you if you add x and minus x, you will at the end exactly get a 0 here, and this is independent of the position of x. So this is a construction for the additive inverse, and in a similar way you can create a construction for the multiplicative inverse. So you have neutral elements and you have inverses, so everything's fine. Second problem is solved. So what's left to do? Well, third problem, I would say it's all the rest. So all the rest is, now you need to prove all these formulas here. So the laws of associativity, the commutativity laws, the distributivity laws, and so on and so on. And this is, well, quite a bit of work. And I want to show you, at least for some of those cases, how the proofs work. So let's start with perhaps the simplest case, which is the commutativity of the addition. So let's focus on that case. And well, we have to prove that a plus b is the same as b plus a. Sounds simple in a way, but adding a and b via the von Staudt construction is not symmetric in the role of a and b. So we somehow have to spend some additional work to get this commutativity to hold here. So this here is how we construct a plus b. So you remember we start with our 0 here and take a and take this line and an auxiliary point. I told you it doesn't matter which we take. We draw these two lines and then form a parallel through b, get another point and get down here. And if we do the same thing with interchanged roles, we get this drawing here. So we start with our line and our point, now connect b to that point, draw a parallel from a to that line and from that point of intersection through that point, and we get b plus a. So you see, b plus a is constructed in a different way than a plus b. So let's just overlay these two pictures and stare at it for a little. And if you stare at it, you notice that a certain sub-configuration stands out here, which consists of these 3 points and these 3 points and these 6 lines. And this sub-configuration is exactly the small theorem of Pappus. And the small theorem of Pappus, since it automatically holds if Desargues' theorem holds, then well, tells you that these two lines have to meet at the same point. So small theorem of Pappus tells us that indeed a plus b is the same as b plus a. Next property. So let's focus on, well, let's take this one here, that the order in which we add doesn't care. And so we want to check whether a plus b plus c is the same as a plus b plus c. So I do the same thing. I do the two constructions in two different pictures, and then I'm going to overlay those two pictures. So first of all, here's again the construction of a plus b. Now we have one more point c here, and we want to add this point to this here, so we have to draw this line here as well and then do the von Staudt construction to get at that point. Completely in the same way, we can do it the other way around. We can first add b and c. So you see this little triangle here gets copied to here, so you get b plus c here, and to that point you still have to add your line, your size a. So in that case, this triangle here gets copied here as well, and you derive at a plus b plus c. So now let's overlay those two pictures and I get the following drawing. And again, if I stare at it, a theorem comes out, and what you see here is that you have a certain instance of the scissors theorem telling you that if you have all those parallels here, then the last coincidence is satisfied automatically. So we get that a plus b plus c is the same as a plus b plus c. And we proved the associativity by applying the scissors theorem, and we can make another check mark here. So let's have a look at this one here. Multiplication is associative, and actually the proof is almost the same, just the role of the labels changes. So please watch the transition of this image to the next one carefully to see how these two proofs are really structurally almost identical. So I go from here to the other case, and you see I only moved my lines, and for the other associativity theorem I can again apply the scissors theorem, which tells me this one is true as well. So how about distributivity? Well, I would say these two things are a little bit trickier for the reason that you have essentially two operations involved. Though actually if you do the proof, you will have to apply two theorems. Actually you need the Desargues theorem and you need the scissors theorem, both of them. I won't do it here in the lecture because the drawing is really quite involved. But try it yourself. It's a very, very, very nice exercise. So, but I want to do at least this one here. So how about commutativity of multiplication? And the reason I want to do this one is not that it is complicated. The reason I want to do it is because it needs some tool we didn't use so far. In all our proofs we did so far, and even in the two I didn't exemplify in that lecture here, you will only need everything below the Desargues theorem. So you will need Desargues, you will scissors theorem, you will need little Desargues and little Pappus, but so far we have not used the big Pappus theorem. So far we got everything except for that here, and but for this one here we really need the big Pappus theorem. So here I constructed A times B, and now I give you the construction for B times A, which is this one here. And if you stare at it, you see that you get a nice subconfiguration consisting of these 3 points, these 3 points, and those lines here. And the big Pappus theorem will tell you that finally those two constructions will meet in the same point. So we will indeed need the big Pappus theorem to prove the commutativity of multiplication. We're done. We did the proof. We got everything together. So we solved our first problem, the well-definedness. We solved neutral elements and inverses, and we did all the rest. So after all, we did the entire theorem. I give you a projective plane in which P holds, and we showed that this is strong enough to find a field in that projective plane. And if we don't have P, if we only have the big theorem of Desargues, then we get at least a skew field. So this was quite a lot of work, and I want to end this lecture with a few remarks and one more interesting proof. And here comes something that I would call the icing on the cake. So the things that makes the theorem even nicer. From a projective plane, we can get a field. If we have a field, this means we can construct a projective plane from that field. So let's take that field and construct a projective plane from that, and it turns out that this plane is essentially, up to isomorphism, our original projective plane we started with. So if you start with a projective plane, create a field from it, and from that field create a projective plane, you will get back the original projective plane. And I will be a little bit sketchy in the proof of that theorem. I first want to refer to the original pages in Hilbert's Grundlagen der Geometrie. So this here is taken from Hilbert, Foundations of Geometry, so Grundlagen der Geometrie. And this is taken from the second edition. And actually this book has altogether at least 10 editions. I don't know whether there is one after 10. So in the second edition, so the argument that Hilbert does boils down to the following parts here. So he defines coordinates for a line, and first goes down to the special case where this line passes through a kind of origin and proves that then you get a kind of linear equation, and then by some other shifts he proves that this line has well, a kind of affine equation. And in one of the later editions of this book, he actually simplified that proof, and I want to sketch how the simplified proof works. So first of all, we need something like a way to get homogeneous coordinates from our field here. And so our field elements were the points on our calculation line. Now I tell you how to get coordinates for an arbitrary point P here. So what we do is we fix a second point on through our origin. So in a certain sense, this here should be the role should play the role of an x-axis, and this here should play the role of a y-axis. So if I give you a 1 here in that part, then I should also give you a 1 on the second axis here, and we can take an arbitrary point here, but we will define this line that connects the two points here. And now I will give you coordinates of your point. So the x coordinate is essentially just if you project down in that direction the intersection with our calculation line. And the y coordinate is essentially the same thing on the other axis. So you project in this direction here, but you remember our field elements were taken from that line, so we have to project down this point to the other axis in a way such that ratios are preserved. So these here are the coordinates for our point, and we essentially say the homogeneous coordinates of our point P are given by those 2 points and a 1 for having a kind of standard embedding. So this is first of all how to get something like homogeneous coordinates, and finally we have to show that if we have a line in that space, so assume you think that P lies on some certain line, then there is a nice linear equation for that line. And this is amazingly simple. So let us start with a point P that lies on an arbitrary line. And let us once recall these are the coordinates for our point P. So this here and this here. And again, we remember we had a 1 here, and well, this time we don't even need the 1 on the other line. What we do is we take a parallel through the 1 here and the line on which P lies, and we get a point here, and we call that point AY. You will see in a moment what role this point AY plays. And now we will do the following. We will take this parallel here and call this point here AY times PX. and we don't even only call that point. Actually, it comes from ay times x, because if you look at it, the ratio between 0 and 1 and 0 and px by this kind of parallelism is the same as the ratio of ay and ay times px. So, as I promise to be a little sketchy in that proof, but trust me, what you do by that is the von Stroud equivalent to multiplying this point here by a number px. So what we are now going to do, we add this p prime y, this length here, we take that and, no, that's not this length, sorry. So we take this length and add this part to it. And we end up at a certain point over here, and we call it, well, the natural name. And actually it is the von Stroud equivalent to that number. And you see that in that picture because we just copied this triangle over there. So we actually did a von Stroud construction on this axis here. But now look closely. Actually, our construction tells us that no matter where our point is, so if we may move point P to a different position, no matter how we do that, this last point here that we get will always be at the intersection of the y-axis and the line on which P was lying. So no matter where P is, we may move it around here as we want. This point here gets always to be the same point, so it is constant. But now look what we have here. This here is an equation telling you that Py plus Ay times Px is a constant number, which is nothing else as a linear equation in the world of our field. So lines are indeed defined by linear equations. So let me move just to exemplify what's going on my point P a little bit, and you see everything moves, but this point here just remains at the same position. So we proved lines indeed have linear equations in that world. So let me close by a few final words that should end this part of our lecture. So we have seen in that lecture that field axioms are essentially the same as the axioms of projective geometry together with P. So whenever we have a field, we can construct a projective geometry from the field. And whenever we have a projective geometry that satisfies Pappus' theorem, we construct a field from that. So both structures are, from a logic point of view, essentially the same. If you like field theory, you must as well like projective geometry, where the theorem of Pappus holds, because it is the same. Every notion of field theory, there will be a corresponding counterpart in the world of projective planes with Pappus' theorem. And conversely, if you prefer to work in field theory, you can translate every concept you have in that world into the world of fields. Though both worlds are structurally identically strong, projective geometry is neither weaker nor stronger as field theory as soon as you have Pappus' theorem. So you see, we really brought those two areas of mathematics, projective geometry and field theory, very close together. From there, we will start to new objects, talking about connects, talking about new kinds of geometries in our lectures, but this lecture finishes essentially the first part of our lecture series. Stay tuned.